Another example of equilibrium with a rigid object is this bodybuilding example. So in this example, the arm is horizontal and weighs 31 newtons. The deltoid muscle can supply 1,840 newtons of force. What is the weight of the heaviest dumbbell this person can hold? And some of this information for this problem is packed into the image here, which I don't find ideal, but it works. So we'll use the image and take that help that it gave us. So as we're looking at this, we first need to identify the object of interest, right? So what is the object of interest? It's going to be the entire arm and the forces that are acting on the arm, right? So the deltoid muscle is one force acting on the arm. That muscle is able to pull because muscles contract. And that's what's shown up here. M for muscle, that is pulled at an angle of 13 degrees. So it's not exactly horizontal, definitely not vertical. What are some of the other forces? Well, the arm itself has some weight. And they show that the weight of the arm is about in the middle there. So that is a force that we're going to consider. It's not negligible. Just holding your arm out, you have to do some work, right? That's not a natural position because it has significant weight. And then if you're holding a dumbbell out at the end there, that weight of the dumbbell is going to be pulling down on your arm, but it's going to be pulling down at the far end of your arm. Finally, the other forces that we have are the actual shoulder joints, right? So your shoulder is able to push horizontally outward, right, against the deltoid muscle that's pulling in. So it keeps your arm from just springing, contracting inward, right? It offers resistance there. And then the shoulder muscle also can provide support up. So for all the things going down, it provides an upward force. Notice in this problem, we don't know anything about the force that the shoulder is exerting. That's one that's harder to figure out because it's a joint, so it's a bone on bone, which is why it's a pushing force here. So what do we do with that? What do we do with this unknown shoulder force that has both an X and a Y component? This makes it harder to sum up the forces in the X and the Y direction because we don't know the shoulder force, in addition to not knowing the weight of the dumbbell. Well, what we can do is we can look at the torques and we can be very careful in how we choose that axis of rotation to make our life much easier here. So in this problem, if we know nothing about the shoulder and the force it exerts, where do we want to put our axis of rotation? That tells us we should put our axis of rotation for calculating torques right at the shoulder joint. Because that way, those shoulder forces aren't going to contribute any torques. That makes our life so much easier. So that's exactly what we'll do. The other convenient thing about placing it here is that they've already defined distances in terms of this left part of the arm, right, where the shoulder is compared to the rest of the arm. So they showed the distance to where the deltoid muscle acts, at least on the arm itself. The deltoid muscle being that upper muscle, right, the triangular one on your arm. Then the distance to the weight of the arm itself, and finally the distance to the very end of the arm where the dumbbell is being held in the hand. 6.20 meters. All right, so if we want to calculate torques, we know that that's going to involve the force times the lever arm for each of these torques. Now, conveniently, the weight of the dumbbell and the weight of the arm are acting straight down, while the arm is purely horizontal. So that already sets up a really nice right angle between the arm and the force. So our lever arms, we can just get from the distances labeled here. So L sub D for the dumbbell, and then this 0.28 is going to be L sub A for the lever arm of the arm. What about this deltoid muscle? We have this distance labeled of 0.15 meters, but notice that's not our lever arm. How do we figure out our lever arm here? Well, for the lever arm, we're going to have to find the perpendicular intersection from this axis of rotation to the force, to the line of action. That's actually going to be something more like that. It's a really small picture, so we could imagine it a bit bigger. There is my line of lever arm, the line of action in blue, and then the arm is horizontal between them. And we have a right angle here between the lever arm and the line of action. It also tells us that angle is 13 degrees. So that's a handy piece of information. And finally, we know the distance of this bottom piece, which notice if we look at the triangle here, this is the longest side of the triangle, 0.15 meters. So if we use the 13 degrees and the fact that it's a right triangle, what trig function helps us out? We want the opposite and the hypotenuse. So this is going to be a sine. The sine of 13 degrees is going to be equal to our lever arm for the muscle divided by 0.15 meters. Once we've identified all our lever arms, we're in really good shape to sum up the torques. So let's get to that. So sum of the torques should come out to 0. Looking at this, we'll have a torque from the muscle, so torque sub m, a torque from the arm, the weight of the arm specifically, torque tau sub a, and then the torque from the dumbbell. So tau sub d, and those all should come to 0. And then we once again need to figure out if it's causing a positive torque for a counterclockwise rotation or negative torque for a clockwise rotation. So notice the muscle, if the muscle is the only thing acting, would be causing that counterclockwise rotation. So that is positive, versus the arm and the dumbbell are both pulling the arm in the clockwise direction. So that would be a negative torque. All right, that's now really good shape. Let's jump over to the solutions that are already written out for us. So here we have labeled the lever arms very nicely, and the sum of the torques is equal to the negative torque of the arm, the negative torque of the dumbbell, positive torque of the muscle. Those all have to come to 0. And just as we found, the lever arm for the muscle is 0.15 meters times sine 13 degrees. So here we know all of the lever arms. We know the deltoid muscle, how much force it can supply, and we know the weight of the arm. Remember, we're solving for the weight of the dumbbell. So we can look at adding this to the other side and dividing by that lever arm of the dumbbell, and then we'll be home free. So taking a look at that. Oop, too far. There we go. We've added the weight of the dumbbell and its lever arm to the opposite side, to the 0 side, divided by the lever arm of the dumbbell. We still have a negative sign in front of the torque from the arm. That's okay, and that's important here. It will be wrong if you don't have that negative sign. Now we can plug in all of our numbers and notice that the meters as units are going to cancel out because we have meters in every expression on top as well as in the bottom. And the units we'll be left with are just newtons, which is what we'd expect for a force. So it comes out to 86.1 newtons, which is about 20 pounds. That seems reasonable. I wasn't sure if it would be, so I grabbed a dumbbell myself, just a 10-pound one. And it's a pretty good amount of work to try and hold a 10-pound dumbbell out there, right? So if someone was conceivably a bit stronger, says that this is a male, so he's likely stronger, then I could see that the limit of his strength is around a 20-pound dumbbell. Some of you might be able to hold more than that out there. You can give it a try. This highlights how we can do the calculation and how torque can make that calculation possible, even without knowing the force from the shoulder joint.